Okay, let's get started. Hello everyone, and welcome to our webinar, Evaluating Moisture Damage with HOBO Temp RH Loggers. My name is Cynthia Selby, and I'm on the Marketing Communications team here at Onset. I will give you a very brief introduction, and then I'll turn over the presentation to our speaker today, Lonnie Haughton of Richard Avelar Assocs. First, I'd like to share just a bit about Onset for those of you who don't know us. We are the company that makes the industry-leading HOBO data loggers that are used all over the world for building performance monitoring, environmental research, and water monitoring. We've been making data loggers since 1981, and we've sold over 2 million of them so far. We have about 120 employees located here in Massachusetts on beautiful Cape Cod, where we design and assemble all of our products. And we have a global network of dealers that serve our customers around the world. The webinar will run for 1 hour, so type your questions into the questions section. We'll save time for them at the end, so make sure you type anytime during the presentation. That section is located on your go-to control panel, and again, type anytime during the presentation, but we will answer them at the end. We are recording the webinar today, and I'll be sending you a follow-up email within a few days with a link to the recording, so you can review it any time at your convenience. And finally, please take just a minute to complete the short evaluation, which will be popping up after you close out of the webinar. Now I'd like to introduce you to Lonnie Haughton. He's the Principal Construction and Codes Consultant with Richard Avelar Assocs, and Avelar Assocs is a forensic, architectural, and construction consulting firm based in Oakland, California. Lonnie's a California licensed general contractor and one of about 850 individuals nationwide who have been certified by the International Code Council as a Master Code Professional. He is the primary author of the paper Qualitative Sampling of the Building Envelope for Water Leakage, which was published in 2007 in the Journal of ASTM International. And since 2009, Lonnie has published a variety of articles and papers that explore the use of humidity and temperature loggers for forensic investigations of moisture damage found within buildings. So I'd like to welcome Lonnie today. And Lonnie, thank you for sharing your time and your expertise with us. And let's get started.
Okay. Welcome all. I'm very excited and pleased to give this presentation. Cynthia has introduced me and our firm, Richard Avelar Assocs. But just as a broader introduction, our firm has about 50 employees. The principal management group is made up of licensed architects and general contractors, and the bulk of the work that we do is related to litigation associated with building envelope performance failures, basically leakage. For those unfamiliar with the phrase building envelope, it simply means the walls, the roof, or the below-grade waterproofing systems that are designed to keep moisture out of the building. And in new buildings, if moisture does come into the building from the outside or damaging moisture occurs from the inside, firms like ours get hired by the parties, plaintiff and defense, that are involved in the litigation. So this study uses photographs and data from an actual investigation to demonstrate how we are learning to use these humidity temperature loggers to assist the forensic team. And what I've realized in the past few years that in different parts of North America, and perhaps very likely different parts of the world, forensic often has different interpretations. And So I always try on a presentation like this to specify that what I mean by forensic is it's the puzzle-solving application of a broad spectrum of technical knowledge and expertise to answer key questions of interest. And in our firm, our questions of interest are where did the water come from, and how, who and how did this failure and why did this failure occur? So this project we consider an apartment complex near San Francisco. It's multiple two-story wood frame buildings clad with pump applied, and I'm going to explain pump applied here in a second. Pump applied 3-coat exterior plaster cement, commonly called stucco, and or some of the cladding systems are fiber cement lap siding. And here's an example of pump applied stucco, because there's many folks have in mind sort of the more traditional application of stucco with a guy with a trowel, and he's troweling it out of a hopper and spreading it around on a wall. This is actually at our shop, our laboratory, and we're actually running some tests of stucco and various flashing systems. So this is our employee, but the purpose of this slide simply is to indicate that in mass-produced housing here in California, throughout the nation, and very likely throughout the world, there are applicators who come in and produce a mix, a stucco mix that is fluid enough that it can be applied, spray applied with a pump. And in this case, for example, this gentleman is applying the brown coat, or actually the scratch coat, the initial coat of stucco. You can actually see on the left panels where he's already scratched it afterwards, and he will let it appropriately cure and then come and apply the follow-up brown coat. This is, for this project that we're talking about, this is a typical building. It's two-story building. Like I say, some of the buildings have fiber cement lap siding and stucco. Others are just pure stucco, in nothing but stucco. And another point of interest as we move along, for mass-produced housing here in California, and I'm sure lots of other areas, the use of sheathing panels, whether it's OSB or plywood sheathing panels, is limited to the structural shear walls. I used to work in Seattle and up in the Pacific Northwest, all walls were sheathed. But here in California, even though our area is so earthquake prone, for some reason we allow builders to apply their sheathing panels only in pre-designed locations. So here's an example of OSB sheathing at this project. And actually we're looking at the inside of the wall and see mold growth, extensive mold growth occurring, and the panel is very wet at the inside of the sheathing within the wall cavity. Here's another example. Now this is an example to show you that it's one of the non-sheathed walls, and we still see there's corrosion, there's evidence of moisture. Perhaps hard to see in this photo, but the building paper here, the asphaltic building paper, is very wet, and the line wire that supports the stucco at the non-sheathed walls is wet. Here's another example where we opened the unit from the inside and took off the interior gypsum board and took out the bat insulation that was in the wall cavity and found extensive evidence of moisture. The interesting thing for us, and for me from a forensic perspective, is that this damage and wood decay and fungal growth that we were finding within the wall cavity was limited to the ground floor walls. These conditions did not occur at the second floor units, and even at the ground floor, the conditions only occurred at certain walls, generally at bedrooms of these apartments that were in throughout the complex. So we still approach the investigation in our traditional way, where we start with the assumption that the water is coming from the outside of the building, which makes the most sense because even in the drought-stricken California, there's still a lot of rainfall that occurs, and construction defects and flashing, misinstalled flashings can allow water to enter the building. But for this project, we carried out a variety of destructive investigations and moisture testing, and conclusively demonstrated that the conditions that you saw in these recent photos did not result from water leakage, rainwater leakage from the exterior. Here again is another example. We've opened a wall. Now we're at the outside. The black material to the left is the asphaltic building paper that was behind the stucco. And we've opened up the OSB sheathing, and inside the OSB sheathing we find evidence of condensation. The water vapor, excess water vapor, has condensed and turned into liquid, and is promoting fungal growth and wood decay. Here's an example showing the outside. Most of what we see here is the OSB sheathing from the outside. We see that it's bright and clean, no evidence of water, but the piece that I'm holding, or one of my colleagues is holding in his hand, we've cut out this one little small section, and you see that area there is the inside of the wall, and shows that there's mold growth and moisture damage at the inside of the wall. So at that point, we're not finding typical rainwater leakage conditions, and wanted to proceed from a different direction to try to understand the conditions we were seeing. So we purchased 100 data loggers measuring temperature and relative humidity, and positioned them within 24 of the ground floor apartments over an extended period, which I will describe here shortly. For this testing, we used the HOBO U23002 Pro V2 loggers from Onset. I'm sure they have other loggers that would serve the same purpose. This is the logger we chose to use for our investigation. And here's a picture of 3 of the loggers. Just in I took this photo to demonstrate what they look like. The great thing about the loggers is they have the logger itself. The brains of the operation is in the main body labeled the HOBO Pro V2, but they have a 6-foot cable that leads to the sensor. And the sensor then, as we will discuss, can be inserted in a different location from the body of the device, which is very handy for a forensic guy like me trying to investigate out-of-the-way locations. And this image I copied from the Onset website, and basically shows how the HOBO logger via a coupler transfers its data over to a portable base station, and then that data is connected to a USB port, which allows processing to occur. So, and as already indicated, this feature, the 6-foot cables, allowed us to drill holes into the ceilings and holes into the walls, small holes, where we could simply insert the sensor to collect data after we've sealed up the holes, and then allow us to come back later and easily, at the end of the testing, 6 months later, to easily to retrieve our materials. So here's an example. We're in a bedroom closet, first floor bedroom closet. We've simply positioned two data loggers there, two of the HOBO loggers. One is the sensor has been inserted up through a hole up into the ceiling cavity, and the other has been inserted through a hole into the exterior wall. And again, this is very, very simple and easy. The only problem that occurred is we used a caulk when we inserted these holes that solidified too hard and made the process of removing the sensor more difficult. That's a simple learning process on our part, and we will next time use a non-hardening caulk. So these next few photos, we're going to show the area that we're investigating, and this whitish material, the horizontal band, is what in our trade is called a belly band, and it simply is covering the rim area between the ground floor unit and the second floor unit. And here's a close-up a view of it. The whitish belly band is off to the left. For this building, what we found, for this project, what we found is that there was not complete sheathing or closure behind the belly band. It simply looked exactly as we see here. There was the polystyrene foam belly band positioned over building paper, positioned over the ceiling cavity that separates the two units, and you can see inside actually the metal work that forms the drop ceiling of the lower unit. The second floor unit then starts in essence at the sill plate that we see higher up the wall. For my purposes, I'm calling this area, this open area that we're looking at, a plenum. And I imagine there's probably mechanical engineers and other folks who could tell me that this technically is not a plenum, but for my purposes and the purposes of my colleague, when I use the word plenum to describe this, they know what I mean. Basically, an open, empty space that is positioned between the occupied portion of the lower unit and the bottom of the second floor unit. Here's another example of the plenum area at a different elevation of the building. Some of the elevations the plenum area was closed. Here we've opened up the OSB, which was bright and clean on the inside, and lo and behold, it's very it's bright and clean on the outside, but lo and behold, it's very wet here at the interior side of the OSB. So this area, this plenum area, is our focus in terms of the testing that we carried out. And here's a plan of, in essence, where our 4 HOBO loggers per unit, typically there were 4 per unit, some we did more, were installed. We installed one out next to the in the hallway next to the kitchen and living room, and then we installed 3 in the closet at the transition between one bedroom and the other bedroom in these 2 or 3 bedroom units. So I will further here. So this is the transition that I'm talking about. This is the same unit behind behind the wall without the window and the wall with the window, and right in the center where the building takes the step, there are closets there serving each bedroom. And we went into these closets. We went into the closets and installed, we see at the bottom of the screen, the first floor bedroom closet. We installed one sensor into the exterior wall cavity. We left one sensor within the bedroom closet itself, just ambient conditions within the closet. And then we drilled a hole through the ceiling board and installed a sensor up into what I'm calling the plenum space. Now, what's interesting here from a forensic perspective is that the wall cavity up to the second floor is continuous opposite the bedroom closet and opposite the plenum space. It would not be uncommon to find at the transition between the bedroom closet and the plenum space to find another section of double plates that would totally isolate the plenum space from the exterior wall. But these buildings were designed with this 9-foot wall, that 10-foot wall that extended up past the plenum space up to the bottom of the second floor. So our loggers were programmed, all 100 loggers were programmed to take simultaneous readings of temperature and relative humidity every 10 minutes. They're all timed the same, so every 10 minutes, 144 times a day per sensor, we collected data. And the purpose of this presentation is just to demonstrate how we evaluated this voluminous amount of data. We're not going to get into who we think made errors. Well, actually, we will a little bit. Later on, we'll discuss one party that clearly erred. But this is an active case in litigation, and we're not going to get into design issues or construction issues. It's simply to introduce how we elected to use the data, the incredible amount of data that we collected. As you see at the bottom of the screen, at the end of 162 days of testing, we had 2.3 million temperature readings and 2.3 million simultaneous relative humidity readings. That's a massive amount of data compared to what I would call the traditional investigative approach by a firm like mine. This is a massive extension of our normal data collection process. So once we collected the data from the loggers, then the HOBO software enables us to convert the temperature and relative humidity readings into the humidity ratio. And this is a key point here, and I'm sure some of the attendees understand this very well, and very likely there are some who don't quite understand it yet, and it's my goal to try to explain what we're talking about. The humidity ratio, in essence, it's the ambient moisture content, and it's measured in our case by grains of water per pound of dry air. Now, obviously, different parts of the world you'd measure with different units, but here, for our purposes, we're going to measure in grains of water per pound of dry air at a particular point in time. The reason this is important to us is because we, in our building envelope performance investigation, we're not interested specifically in relative humidity. We're not interested specifically in temperature. We're interested in water, actual water. How much water, or in this case water vapor, how much water is there? If there's more water in one location than another, then very likely the area that has the most water is a major player in the water damage that has occurred, whereas the area that has least water is a lesser player. And this would be no different than say a normal practice that a firm like ours would do would be to take a pin-style moisture meter and go to wood or OSB plywood sheathing at a wall and measure the moisture content ratio of the plywood sheathing, and perhaps at one location we find that it's 18%, and at another location we find that it's 24%. Well, the identifying the wettest areas of the plywood sheathing or the stucco or the interior gypsum board points us towards where the problem is occurring. So all we've done here with this analysis is we are now measuring the moisture content. It's called the humidity ratio technically, but consider it the ambient moisture content of the air, and then we're going to track the changes in the ambient moisture content of the air over time. So for me, the book that best taught me and explained to me the humidity ratio, psychrometrics, relative humidity, the entire process was this book by Donald Gatley, Understanding Psychrometrics, published by ASHRAE out of Atlanta. It was the perfect book for me to understand what I needed to know. And as he points out, the humidity ratio is simple, effective, convenient way of accounting for the mass of water vapor, the actual the actual amount of moisture that is in the air, by relating it to the non-varying mass of dry air. So the higher the ratio of water, the more water there is, and this is a valuable forensic clue. So this is a very simplified psychrometric chart, and I assume many of the attendees understand this very well, but we'll touch on it briefly for those who may not. And the psychrometric chart was invented a long time ago, the advent of air conditioning, and certainly one of the things that's a tool that's changed the world in many ways. But the psychrometric chart, this is a simplified version. It uses temperature, which is the vertical red line, and relative humidity, the percentage relative humidity, which is the curved blue line, and where the two intersect, the horizontal green line that goes off to the side gives us the humidity ratio. And in our case, we're doing it in grains per pound. Often this is done in pounds of moisture vapor per pounds of dry air, but it's far more convenient to approach this in grains per pound. And here in the United States, in our way of measuring, there are 7,000 grains in a pound. So here's a close-up version of the same psychrometric chart, and just as a just say as an odd example, if we had 80 degrees temperature, which is the vertical red line, and we measured 40% relative humidity, and then followed where the two lines crossed, which is approximately 40%, where these two lines cross, we extend that horizontally off to the side, and we find that we have a grains per pound ratio. This is actual moisture content ratio of 60 grains per pound. So then we can compare that amount of moisture with the amount of moisture at a different time of the day or a different part of the building or a different building, compare various buildings, and we can see which is wetter, and that difference, as we'll see in some of the graphs I'm going to show you, is a invaluable provides invaluable information. So we're going to quickly just go through. Here's my screen on my HOBO U23 logger. We start off with temperature and relative humidity have been checked. I set my logging time for every 10 minutes. I then, when I collected the information, I added the data assistant, the grains per pound data assistant. You see it checked up here at number 4. So the software is converting temperature and relative humidity, just like we saw on the psychrometric chart, converting it over to grains per pound, which then presents this information in this massive graph or a massive amount of data. Now, this is a 67-day testing period that we did at phase 1 of our testing. The great, I'll throw in now that a great thing occurred for our testing purposes is California is suffering a major drought, and during this past year, and during this period of 60 days of testing, we only had the barest amounts of rain. So that allowed us to basically eliminate rainfall from our analysis of what was occurring. Now, we'll see later on in this presentation that then later in our testing, we were then able to see what happens when the rainfall returned. So then what I do with my the information I've received from my HOBO loggers, I then export the table data, Control E, and I'm exporting it into a simple Excel spreadsheet. And the reason I'm doing that is because in the world that I practice and in the litigation arena, I need to use software and analysis that everyone is familiar with. And so everyone is familiar with the Excel spreadsheet. So I'm taking the data from the HOBO loggers and I'm converting it to the Excel spreadsheet. And as we can see here, for example, with this data logger number 566, after 9,809 readings, we can see the average temperature that we measured is 71.48, the average relative humidity, and also the average grains per pound. The grains per pound, even though we see a reading of 78, the average grains per pound after 9,000 readings in this unit was 66. So here we are. And now I'm going to show you an example of how I used the information. Here's an apartment A, where we see massive spikes inside. This is the interior air within next to the kitchen. We see massive spikes of moisture content that occur on a regular basis. This is cooking and showering. That logger was next to the bathroom shower. A bathroom shower. It was next to the kitchen. This is very typical of what you see inside an occupied unit is a massive spikes of moisture, which I don't care so much about as I care about the average. How wet is this unit on average? On average, its grains per pound was 54. And before I move from this slide, if you look over to the right of the slide over around 7633 on our readings, you see a multi-day period where there was very minimal moisture being generated in the unit. This was the Christmas holidays. These folks were gone from their apartment for a 3-day period, and then they returned. As you can see, the day they returned, they took showers, did cooking, and got back to business. So this information is very precise and very informative. Note again that we have an average grains per pound of 54. Here's a similar unit, same apartment complex. They have an average grains per pound ratio of 72. It's a far wetter unit. And a forensic question, which we're certainly not going to try to answer here, is why is it a wetter unit? Are there more people taking more showers, doing more cooking? Do they steam rice 4 times a day? There's numerous options, including perhaps construction failures or plumbing leakage. There's many explanations for why a unit can be wetter. I'm just demonstrating here that one unit was far wetter than the other unit. So here, now we've gone into the exterior wall of apartment C and apartment D, 2 separate apartments. We've logged data at the very same time, and we see that unit C at the top, we're measuring this in grains per pound, and we've taken these readings are taken every 10 minutes. We see that the apartment C, the exterior wall, is 75% wetter on average at unit C than unit D. Why is that? Well, we're not going to answer that here, but that's a very key forensic question for our analysis, is what's the difference that could possibly explain that? Here's an interesting one, apartment F. So there's just 17 days of data, and we could see on day 7 they vacated the apartment, and you could, even if I didn't know that personally, I could see that from the data. We tracked their moisture generation within the unit when they're cooking and sleeping and bathing, and then we see they moved out, and they this is the red line we're talking, but then the blue line is what's happening within the exterior wall cavity. And there's 2 points of interest there. One is that there's very little correlation between what's happening in the exterior wall cavity. We see that it does decrease a little. The moisture content within the wall decreases a little when they move out, but it's not that significant. But we also see that there's a spike in moisture every day. Every one of these waves we're seeing is daily. It's a daily spike in moisture content within the wall cavity. So what we did here is, this is the same wall cavity. The red line is the same wall cavity, and we're tracking grains per pound. The black line is exterior temperature with a different logger, actually even by a different manufacturer, taken 1,000 feet away from this apartment. And what we see is a striking correlation between the amount of water content, water vapor, during particular times of the day, or actually with a striking correlation in all days, between the exterior temperature and the moisture content within the exterior wall cavity. We see at about 4753 on the sheet that an extended cold period for a week occurred. The weather got very cold. Our drought continued, but the weather got very cold, and the moisture content within the exterior wall decreased. We're going to explain that here shortly. In this slide, we're still at Unit E, and we're comparing the moisture load in the bedroom, which is the blue line, and the moisture load within the exterior wall. So in the previous slide, we compared the moisture load, the ambient moisture content outside, with what was occurring within the exterior wall. And now we're comparing the ambient moisture load inside with what's occurring in the exterior wall. This, from an overall analysis, provides very fascinating quantity of information. So then we ask ourselves, what occurs within these exterior walls during hot, sunny weather that follows a rainy period? And fortunately for us, towards the end of our testing, our drought was relieved for a bit, and we had a couple inches of rain, several inches of rain in this area, followed by increased sunshine. We see here that here's an east-facing wall. We're taking the readings within the wall cavity, which is the red line, within the closet, which is the purple line, and within the plenum space, which is the green line. And what's fascinating is that when the sun returns is when the moisture content within the wall cavity spikes during the middle of the day. And here's why. When the rain occurred at this wall, this is fiber cement siding, leakage occurred around this flashing. This is that belly band we talked about that has the foam insulation. Leakage occurred at this flashing, at the end of the flashing, and then was heated by the sun and blown into the plenum space. And the reason that a problem that we found throughout the complex was that flashings, at these metal flashings at these transitions were not caulked. So the purpose of the flashing is to keep water from entering the building envelope, but because the contractor failed to caulk the joints, he allowed water to enter into the wall assembly behind the stucco, which then, or behind the belly band, which then was heated by the sun, as we saw on the graph, and blown into the, pushed into by solar pressure, by the heating, solar-driven diffusion was pushed into the wall cavity. So here's another example. We find a remarkable correlation between the sunny weather and following rain and the spikes of moisture. In this case, the spikes of moisture that occurred about 1 or 2 or 3 in the afternoon at the heat of the day within the plenum space, within the exterior wall cavity, and also within, which is the red line, also within the green line plenum space, and to some degree even within the closet. So we can see proof here that a construction defect caused increased moisture content within these walls that have a damaging amount of fungal growth. That graph we just saw was taken at this wall, which we looked at earlier. We did not open this wall, but I'm very confident that if we came and did destructive testing, examination at this wall and took apart the belly band, we would find that rainwater, during rainwater events, rainwater coming down the upper wall intrudes behind the foam belly band and is trapped there at certain locations, where then later it is heated by the sun and driven inward. So the summary slide here. From my perspective, a forensic perspective, what this tells me is that moisture as water vapor is always entering these exterior walls from both the interior during heated periods and from the from the exterior during the heated periods, and also from the interior when these periods of massive moisture generation occur. So when we have leakage in a wall, we generally have water damage in a wall. There are ways that we typically evaluate typical conditions. But in this case, we had a complex with atypical conditions, and actually atypical design, that continuous wall that spanned between the bedroom closet and the plenum was atypical design, and atypical construction in the sense that at a minimum the party that installed the sheet metal flashing has to be criticized. And what I'm trying to then demonstrate here is that these temperature humidity loggers can and did provide valuable forensic information for us to use in conjunction with some engineers we hired and other parties to produce our overall analysis of, for litigation purposes, of what occurred at this building. And that's the end of the presentation.
Wonderful. Thank you. Thank you, Lonnie, very much. That was very enlightening. Let's take a look at some of the questions that have been sent in. And folks, please be sure to type in your questions in the questions section. And we'll have Lonnie here with us for a few more minutes, and he'll be able to answer. Let's see. Lonnie, do you want to begin?
Yes.
Okay, go ahead.
So there's a question of no outside sensor. Yes, we had 4 outside sensors scattered throughout the project, and actually from a different manufacturer, and we just did that so that nobody would claim later that there was some, I don't know what they claim later, but yes, we did have outside sensors and throughout the project, and all 4 of these outside loggers produced the same amount of information. And there's a question here: rainwater getting into the wall cavity behind the belly band. Wouldn't it be preferable to use a flashing detail that didn't rely on caulk to work? Yes, but we're our role coming in from a forensic perspective is part of our firm does design, but from a forensic perspective, we're asking ourselves what went wrong. And here it's very obvious that this flashing detail, whether or not it was the best, it certainly wasn't installed as performed. So we have a question. So you had to go to each individual sensor to download its data, and that is true, but it's a very simple process. You take what's called this portable shuttle. We showed you a picture of it earlier. You walk into the unit. You're not disturbing the sensor in any way. You're grabbing the brain box of the device. You hold this shuttle up to it. The transfer process takes 30 seconds. So for us, going into each unit and processing 4 loggers generally was about 8 to 10 minutes each, and a lot of that was just talking with the tenant and explaining what we were doing. When you extract the data, you actually are just basically extracting the data from the hard drive, and the sensor continues on its merry way. There's a question: is there a rule of thumb for maximum humidity ratio to be a problem? I don't know of any. So what we've done here in our office is, for here in the San Francisco Bay Area, we have our own sort of informal rule of thumb that that I hesitate to say that would be valuable or would be worthwhile for other areas. I think the huge issue with defining the humidity ratio is you need to understand the quality of the construction. If this is a very well-built building, then you can handle a higher amount of moisture on the inside, because it's not going to find the various routes that allow it to enter the wall assembly. If it's mass-produced construction where these buildings are being churned out like cookies from a cookie cutter, then then it's lesser amounts of a lesser moisture content can still cause a problem. So there's no hard rule of thumb. I think it's something that if some other area, part of the country, they would need to sort of sort it out on their own. And that's the same in terms of where mold or other moisture damage begins to occur. Mold and moisture damage occurs in these walls or at the interior face of the gypsum if it gets cold. So if we've built a tight wall and properly insulated it, then we can again handle much more moisture on the inside than if we have a wall where there's massive amounts of cold airflow during the winter. There's a question: is the belly band just a facading on the wall face? Well, yes, it is, and often here in the San Francisco Bay Area, and similarly when I worked up in Seattle, the belly band would actually be positioned. It's just a facade, and it would be positioned over the stucco. So you'd have a continuous plane of stucco from the top of the building down to the bottom. In this building, I certainly would not recommend this to anyone. In this building, they interrupted the stucco and just stuck this belly band into the face in some locations, or in others they stuck it over part of the brown coat, but it was still or scratch coat, but it was still interrupted. There's a question: at the right exterior temperature, would an IR camera shots of exterior provide you additional information? Yeah, that's exactly right. This is the kind of stuff that of information that certainly an infrared camera could provide very invaluable additional information. Then does the time base stamp drift between separate sensors cause an issue after a long logging period such as 6 or 12 months? There's no drift between the sensors, and to our knowledge, we certainly have found no evidence of any drift between the sensors, but we're also in the process of when you go and take the data from the logger, your shuttle, which has been synced with your computer, is also syncing the loggers back together. So if there's even a small difference in terms of seconds or anything like that, they definitely are being synced. Is non-condensing moisture still a problem in buildings? Is a question. Certainly, there's rainwater into buildings and massive leakage and plumbing leakage. They certainly there's certainly cause massive problems. And then here's a very good question. So were the apartments that were monitored chosen because of tenant complaints or based on the most likely place for water damage to occur? And basically it was some of one and some of the other, and some that were just available. The tenants who were aggressively complaining, if it was too aggressive on their concerns about interior moisture, they got vacated from the units. They were moved to other units, and we chose those because they were vacant and therefore less disruption to the tenants. And then others we chose to make sure that we had enough of the same type, and our choice of positioning the loggers within the closets was 3 of the loggers within the closet was twofold. One, because it was these bedroom walls that were experiencing at the ground floor apartments the most damage, or the most problems. But but it wasn't occurring at all of the ground floor apartments, and also because it was the most convenient. We wanted a place where we could stick the loggers, store them away, and the tenants weren't going to bump into them, or a kid was going to come and play with them and throw it in their fish bowl or whatever. And so the upper back corner of their bedroom closets allowed us to access to the ceiling cavity, access to the exterior wall cavity, access to the interior bedroom air, and was totally out of the way and was adjacent to those walls where water damage was occurring. Next question. This is, how about us that can't or don't do destructive testing, maybe just BD and IR and want to follow up with RH logger? Sure, absolutely. I think that this investigation, we were able, for various reasons, to come in and do a very sizable amount of destructive testing. And but we would certainly, these loggers would be invaluable and associated with IR testing, for example. And said, won't you always have a moisture problem with large cyclic temperatures? Well, if we're talking the exterior wall, there's lots of exterior walls, even at the second floor of these buildings, where clearly the same stucco-driven cycle, the solar-driven cycle of the stucco being heated, absorbing water, or even water that rainwater that gets behind the fiber cement siding is going to be pushed inward. That's just part. It's clear that that's what's occurred for generations, hundreds of years. The issue is whether or not, where we have the problem is where we're adding more water to what's a normal process. It's normal process that water vapor movement, diffusion, whether it's from the outside or from the inside, is occurring in their walls. The problem occurs when we're increasing that amount of moisture, either with construction defects or via large amounts of tenant lifestyle issues. There's a question here, do we think about the relationship between humidity ratio, air, and water activities of materials? Sure, but for my purpose here and of this discussion and this analysis is, this is coming in and using this massive amount of data to get a forensic snapshot of what's occurring, and then from that forensic snapshot and these 2 million each temperature and relative humidity readings, then we can bring in mechanical engineers, for example, or material scientists, and all of that actually usually happens in the course of the litigation. And then finally, what software syncs the loggers set to different intervals? And the loggers are synced by the HOBO software, and then they're resynced when we sample them. If we take the data, they get resynced. And if we wanted to or the loggers we use by the different manufacturer, they were all synced by my computer at the same time. And of course we could set loggers for different intervals, 10 minutes, 2 minutes, an hour. A lot of mechanical engineers I find seem to come in and only sample once an hour. I find that once every 5 minutes or once every 10 minutes, while it produces massive amounts of data, is far more informative to tell you what's occurring throughout the day in the project. And that's the final question.
Well, that's wonderful, Lonnie, and I really appreciate your sharing your time and your expertise with us today. I think everybody appreciates it as well, and hopefully everyone has a great day, and thank you all for joining us.
And let me jump in if I can. If anybody wants to ask a follow-up question, please send me an email. It may take me a few days to to get back and respond, but I'd be happy to communicate with other interested parties.
Absolutely, and the contact excuse me, the contact information is on your screen, and please reach out to our Onset application specialists. They're here to assist you and can certainly help you choose an or rather a logger that will suit your application. So thank you all, and have a great day.
Bye all.